Hello everyone, welcome to Deeksha Karnataka YouTube channel, and you are watching Masterstroke, where we are basically discussing each and every chapter from all subjects so that you are prepared for your KCET as well as your PUC exam. So you can take this as a theory lecture where we are discussing the theory in detail, in depth. So if you are willing to score a good rank, especially a rank below 1000 in KCET, as well as if you want to score a good marks in your PU board exam as well, then definitely you should watch this lectures continuously without any pause, and we are trying to give you the lecture as short as possible so you can revise the chapter, you can learn some mistakes that you had done, that was you are doing in the past. So everything will be covered. Also, I am going to give you the consolidated formula sheet chapter wise. So if you watch this lecture, once the lecture is over, you can download the PDF will be shared exclusively through our WhatsApp channel. So don't forget to join the WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. You can click on the read more and then you will get the WhatsApp channel link. Once you click on that, you have to click on the follow so that you don't miss out on any update. Also, if you are watching this channel for the first time, or if you have forgotten to subscribe to our channel, don't forget to subscribe, because everything till your KCET exam and COMET exam, this channel will be very, very important for all of you. Now let's start. So first we are going to discuss what is that list of topics we are going to discuss. We are going to discuss electric current, Ohm's law, resistance and resistivity, drift velocity, combination of cells, KCL and KVL, that is Kirchhoff's current law and Kirchhoff's voltage law. Right, let's start. First we will start with electric current. So what is electric current? Many of you already aware that if a conductor is carrying current, conductor carrying electrons, then it is called electric current. But the definition is slightly tricky. The net amount of charge small q flowing across the area in the forward direction in time interval t, then the current is given by I equals to q upon t. So the charge divided by time is current. Okay, so charge divided by time is current. Now the unit of current is ampere, dimension of current is A, and it is a fundamental quantity. Okay, current is considered as one of the 7 fundamental quantity. Currents are not always steady. So if you are wondering that current is constant, current is not always constant. For example, the current that we use in our homes is actually an AC current which fluctuates 50 times every second. Okay, so the fluctuation is very high. So that's why if you want to measure a current which is fluctuating over time, then this is not correct. The formula that you have to use is dq by dt. What is dq by dt? It's same as differentiation of charge with respect to time. Okay, charge generally varies with time, and if you know the function, you can differentiate it and you can calculate the current. Okay, so this formula is very handy for KCET preparation. Now let's continue with electric currents in conductors. Okay, so we know that there are 3 types of materials. One is conductor, another one is insulator and semiconductor. There are 3 types of conductors, right? So when you are talking about conductors basically means metals, mostly metals, and few non-metals also are good conductors. For example, graphite is an example of non-metal being a good conductor. Electric charges experiences a force in the presence of external electric field. So if there is an external electric field, okay, then it experiences a force. This is not from this chapter. We have learned this in the electric charges and field chapter, that if you put a charge inside an electric field, it experiences a force. If the charge is positive, it experiences a force in the direction of the field. If the charge is negative, it experiences a force in the opposite direction of the field. Right? So these are everything. These things are known. Right? So if this is an electric field, okay, this will be force, this is also force, this is minus force, this is I am saying plus force. So if the charge is positive, it experiences a force in the direction of the field. If the charge is negative, it experiences a force in the opposite direction. Right? electrons being negatively charged move opposite to the direction of the electric field, right? Electrons are negatively charged, so if you apply electric field, then they will move in the opposite direction. Now, metals have large number of free electrons. As I mentioned, conductor means, in this chapter we will specifically mean metals. So metals are conductors, they have a large amount of free electrons. Free electrons means what? So these electrons accelerate in the presence of external electric field. Okay, so one thing you have to understand, we have discussed in electric field chapter as well, these electrons are free, but they are not allowed to leave the metal. They has to stay within the metal, even though they can move within the metal freely, but they are still bound inside the metal. Now if you apply an electric field around the metal, okay, then these electrons tend to accelerate. Obviously, if there is a force, there will be an acceleration, right? Force is equals to acceleration. Why? Because our grandfather Newton told us that father equals to ma. Okay, so F is equal to ma. So if there is a force, there will be an acceleration. Okay, now Newton is a grandfather of physics. This gives rise to the electric current. So when you apply electric field around a conductor, okay, if you apply a electric field around a conductor, electrons tend to move in the opposite direction. Okay, so electrons tend to move in the opposite direction, and because we consider the motion of the positive charge to be conventional current, okay, electrons are moving in the opposite direction, but we consider the motion of a positive charge as conventional current. What happens is that we say that current is moving in the direction of electric field. Now how you can apply electric field? By applying potential difference. Okay, so if you apply a potential difference, we know that electric field is related to potential difference. How? So we know that electric field is minus dV by dx. Okay, so Ex is minus dV by dx. So if you apply a potential difference across a conductor, so dx is already there, this is the dx part. Okay, the distance is dx. Okay, and if you apply say plus 10 volt here, minus 10 volt over there, then the potential difference is 10 minus 10, that is 20 volts. Okay, so the potential difference you apply and the electric field will automatically be generated in the conductor. Okay, so many students think, what is the relationship between potential and electric field? Actually, electrons are moving because of potential difference, but in this chapter we will mainly focus on potential difference rather than electric field, even though electric field is the cause of electric current. Okay, without electric field there will be no electric current, and that electric field is related to electric potential, and that is why even if you apply a potential difference, that in turn produces electric field, and that electric field actually responsible for the motion of electrons. Now let's move on to Ohm's law. Now Ohm's law, here we will relate the potential difference with current. Okay, so as I mentioned, electric field is the major thing that is producing the current, but still in this chapter we will restrict ourselves within the potential difference only. So, and Ohm's law is the first law which was given linking electric potential and current. Okay, and when this law was given, electrons were not yet discovered, so it was assumed that the positive charge is moving across the conductor. That's why conventional current direction is in the opposite direction. Okay, if had electron been discovered, then maybe we had entire book of our entire books may have a different direction. Okay, but anyway, whatever happened for good. So let's see. If temperature and other physical conditions remain same, so these are the two constants of Ohm's law: temperature and physical conditions. Physical condition means physical state. Okay, suppose you are applying current through a conductor, suddenly the conductor melts, then it will become a liquid. Okay, so that means it is no longer in the same physical state as before. Okay, physical state also refers to its dimensions, length, breadth, area. If you change them, then again Ohm's law will not be valid. Okay, so physical condition, obviously the variable will change. Okay, so exact form may not be valid. Now so Ohm's law is basically something which states that if these two conditions are constant, then the current through a conductor is directly proportional to the applied potential difference. Okay, so the current is directly proportional to the applied potential difference, and you can simplify this to be V equals to I into R. So R is the constant of proportionality. Okay, so here R is the constant of proportionality, is called the resistance of the conductor. Now what is the meaning of resistance? Okay, those who are fans of anime or movies, okay, there is a very common term that they are the resistance. Okay, there is a movie called Terminator. Okay, in the Terminator series there is a faction of people, they are being called resistance. Okay, resistance against the machine that they are trying to take over the world, right? So we all know that resistance is something which tries to resist, which tries to stop what is going on. Okay, so metals, even though they are good conductors, they are not very happy that electrons are allowed to pass through them freely. Okay, so electrons are metals are not very happy that okay, you are allowed to pass through me without any effect. So that's why even though metals have low resistance, they do have resistance. Okay, they try to stop the electron passing through it. Okay, they will say okay, don't go, give me some toll tax. That toll tax is this resistance. Okay, so resistance varies from material to material and based on some other condition as well. Okay, the SI unit of resistance is ohm. Okay, its symbol is given like this. Okay, like a cap. Okay, this is called omega. Okay, and demonstrated by the symbol omega, the resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. So how big the conductor is, how area is more or less, length is more or less, based on that resistance can vary. Okay, now there is one more important thing, is that this is the general form of Ohm's law. Now we have stepped up. This law we have learned in our class 7th or 8th standard. So in now class PUC 2, other form of Ohm's law is given by J equals to sigma E. J is equal to sigma is the modern form of Ohm's law. Here J is the current density, sigma is conductance, and E is electric field. So as I mentioned, electric field is also there, right? Electric field is the responsible reason for the motion of current. So that's why there should be a formula which relates the current to electric field. Okay, so electric field is E and J is current density. J is basically current density, means current per unit area. Its unit is ampere per meter square. It came in PUC exam, final exam once. Okay, so unit of current density is ampere per meter square. Dimension is AL to the power of -2. Now let's move on. Before moving on, I just want to remind you that if you are preparing for your KCET and if you are wondering how many questions to practice, from where to practice, and how can I be able to solve all the questions in time, then ABHYAS KCET 2026 test series is here, which will help you to prepare more for your upcoming KCET exam. How it will help you to prepare for KCET exam? This basically has 35 KCET level test. Okay, the level of the questions are exactly same as KCET. Obviously the questions, if you practice these questions, will the questions be common? 99% they will be not. Okay, but will the concepts be repeated? 100% yes. Okay, so the concepts that is being given in these questions will be definitely be helpful, first of all. Secondly, you will get the questions, you have to answer those questions in 60 minutes. Okay, which is very important for you to practice the time management. Okay, 60 questions if you practice in 60 minutes, then if you practice it now, in exam you will get 10 minutes extra more. So you can utilize that 10 extra minutes. First of all, you have to why you are getting that 10 minutes extra but we are giving you 60 minutes only, because in the exam you have to circle the OMR sheet. To circle the OMR sheet, they are giving you 10 minutes extra, and that 10 minutes extra can help you to answer 2-3 extra questions as well. What else? This year we are going to give you free KCET PYQs, absolutely free of cost, and not 1 year, not 2 year, not 5 year, but 10 years KCET PYQs. Okay, and they are all of the PYQs are from the current syllabus. Any old syllabus questions which are there in the some of the PYQ books which confuse the student. Okay, sir is not teaching this concept, but it is there in the PYQ. Okay, so why sir is not teaching it? Because that is deleted. Okay, those questions are deleted, they are not part of the syllabus. So we are going to give you exactly the questions which are currently part of the syllabus along with 35 KCET tests, and you are going to get this for absolutely almost bargain 1499. So if you are still wondering that whether should I consider a purchase or not, you have to do it, think about it seriously, and if you still have not make up your mind, you can still get 4 free tests absolutely free, but you have to register yourself and use it through our app only to access the 4 free tests. Okay, now let's continue with our discussion. So now we will see how resistance varies with the dimension. Okay, so resistance here, as I mentioned, resistance depends not only on material but also it depends on the dimension. So resistance equals to rho into L by A. What is rho? Rho is called resistivity of the material. Okay, resistivity, sometimes it is also called specific resistance. It is also called specific resistance. Okay, it is called specific resistance and it depends on the material. Okay, rho depends on the material. Resistivity is independent of the geometry of the material. It varies from material to material and on the temperature. Okay, now as you can see, resistance directly depends on length and inversely depends on area. Okay, resistivity is directly proportional to length and inversely proportional to area. In some cases they might give you diameter and they might ask you what will be the resistance. In that case, from diameter you have to calculate area. Circle, okay, circle's area is pi r square, so diameter is given, so it will be pi d square by 4, right? So you have to adjust yourself, adjust your learning. Physics ends over here, mathematics and geometry starts from here. Okay, so you have to remember that as well. Now let's move on to temperature dependence of resistivity. How resistivity depends on temperature. First of all, resistivity directly proportional to temperature. So rho T at any temperature T, we are taking Celsius scale. Okay, rho T equals to rho naught. Rho naught is the resistivity at 0 degree Celsius. Resistivity at 0 degree Celsius, and rho T is resistivity at any higher temperature T. Then it is given as 1 plus alpha T minus T naught. T minus T naught or delta T. Okay, so the same formula is applicable for resistance as well. If you apply the same formula for resistance, RT equals to R naught 1 plus alpha T minus T naught. Generally T naught is 0 degree. Okay, generally T naught is 0 degree or base temperature. Okay, this is the formula for resistance. Okay, and here alpha is called temperature coefficient of resistance. Okay, so temperature coefficient of resistance is also dependent on material. So different materials have different alphas. Okay, alpha is not constant for all materials. It is dependent on the material to material. So rho is dependent on material as well as temperature. Now alpha can be calculated from this equation as alpha equals to rho T minus rho naught divided by rho naught by T minus T naught. Okay, in terms of resistance, alpha is given by RT minus R naught divided by R naught T minus T naught. So if you simplify this equation, you can calculate alpha from this question. Okay, resistance at two different temperatures. Now many cases temperatures that will be given to you are not 0 and say 100 degrees. Okay, it will be given say 50 and 60 degrees or 50 and 100 degrees. So how to calculate in that particular case? So in that particular case, alpha or temperature coefficient of resistivity is given by RT2 minus RT1. Okay, higher resistance minus lower resistance. How can you remember? Higher resistance minus lower resistance divided by lower resistance times higher temperature minus higher resistance into lower temperature. That's how you can calculate alpha. Now let's see one numerical question. Okay, the resistance of a conductor is 5 ohm at 50 degrees Celsius and 6 ohm at 100 degrees Celsius. Its resistance at 0 degrees Celsius is. So very interesting question. First of all, you can calculate alpha from this problem, and you can calculate what will be the resistance. Okay, so or one more thing you can do, that because alpha is same, okay, alpha from the first given information, what is the formula I told you? Higher resistance minus lower resistance divided by lower resistance times higher temperature minus higher resistance into lower temperature. Okay, this way you can remember. This is the alpha. Okay, now if the resistance, say, at 0 degrees Celsius is X, resistance at 0 degrees Celsius is X. Okay, obviously it will be smaller than that of 5 ohm, right? 5 ohm is at 50 degrees Celsius. So same way we can write alpha twice, one from the given information, one from the unknown variable. Okay, and then we can compare these two. This is the way to solve it. So 5 minus X divided by X into 50 minus 5 into 0. 5 into 0. Why 0? Because 0 degree is the temperature at where we are trying to find. Now if you compare these two equations, you will be able to find X. Very easy, right? So now let's simplify. 6 minus 5 is 1 divided by 500 minus 300, and that is equals to 5 minus X divided by 50X. Okay, now cross multiply. First of all, 1 by 500 minus 300 is 1 by 200. So 1 by 200 equals to 5 minus X divided by 50X. Now how can you improve the speed? So instead of writing this step, if you can multiply 200 directly to this value, then you will be slowly improving the speed. Okay, instead of writing alpha once 1 2, if you write the equation once at once, then you can improve your speed. So I hope you understand the problem. Okay, first we have taken 6 ohm and 5 ohm, next we have taken 5 ohm and X is at 0 degree, and applying the same formula. We have applied the same formula twice. Because alpha is constant for a given material, so we can say these two equations also has to be same. Right, now cross multiply, we get 50X equals to 2 into 5 is 10, so 1000 minus 200X. Okay, or 250X equals to 1000, or X equals to 4. Okay, X equals to 4. 250, 1000 will be 4. Okay, now this minus 200 came over here and become plus. So if you are still wondering, so correct answer is 4 ohm. Now this is an easy question. In exam, suppose you are finding a slightly tricky question, you should remember this formula. This formula is very handy to remember, this formula. Okay, now let's move on to the next portion. Drift velocity and mobility. There we have some relations to remember. Okay, based on these relations you might see some questions. First of all, drift velocity. What is drift velocity? So as we know that when a conductor is being subjected to external electric field, it produces electric current, right? Electron starts to accelerate. But is this acceleration is correct? The term acceleration is correct? Actually no. So even though the force is acting on the electron and electron is trying to accelerate, the material or the conductor itself trying to resist the motion. Okay, so there is a force, there is a resistive motion as well. So in return, what happens, the electron, instead of moving with acceleration, they move with a constant velocity. Okay, they start to accelerate initially, they attain a constant speed, and then the resistance force from the opposite direction stops the acceleration, but the electron still moves with that constant speed. It's like a terminal velocity. If you remember terminal velocity in viscosity chapter, okay, so electron starts to accelerate, then attains a certain speed and they move with that constant speed, and that speed is called drift velocity. Drift velocity, what is the significance of drift velocity? It is similar to a ball floating in an ocean. Okay, if you visit ocean, for example, there are a lot of oceans around Karnataka. Okay, the entire west part of Karnataka is full of ocean. Mangalore, okay, Mudreshwar, you may have visited one of those places, Gokarna. Okay, so there you have seen waves coming, right? So if you throw a ball into the wave, the ball moves along with the wave. Okay, and that motion is called drift. Okay, the ball does not have in its own speed, but it is being carried by the wave itself, and it moves along with the wave, and that is called drifting. Drifting means it moves endlessly without any particular aim. Okay, so this is called drift velocity. Electrons do drift from the negative side of the battery to the positive side of the battery. Okay, because we are considering a circuit, right? So if you consider a circuit, so electrons drift from negative to positive. Current is flowing from positive to negative, so electrons drift in the opposite direction, from negative side of the battery to the positive side of the battery. But the speed is very slow. The motion of the electric charges, the electrons, are very slow. But have you ever wondered, drift speed is slow, but if you switch on the circuit, or say you switch on the light, it glows immediately. But the electrons which are there in the switch, they take maybe 5 minutes or 10 minutes to reach the lamp. So the exact motion of the electron is not important. The important is electric field. Electric field travels in the speed of light, and that's why you are able to get the light almost immediately. So electric field is important, not the actual motion of the electron. So anyway, drift speed normally is given by minus small e, that is charge of electron, into electric field divided by mass into tau. Okay, tau is called relaxation time. So relaxation time is what? Again, so suppose electron is moving from one end to other end. Okay, they are colliding with other electrons, and that gives rise to the resistance. Okay, so during the collision, electron slows down, and it again moves further because of the electric field. Now between two collision, there is a time gap. So that time gap is called relaxation time. If you take the average of all such time, then you get the average relaxation time, that is tau. Okay, average relaxation time is tau. And in terms of current, this is the most important formula, that is I equals to NEA VD. NEA VD. NEA VD is drift velocity, so N is the number density of electrons in the metal, which is usually constant. E is charge of an electron, is again constant. A is the area of the current, area of the conductor. Now from this you can show that for a conductor carrying constant current, A into VD is constant. A into VD is constant. So if you have a conductor of different surface area, suppose this is area A, this is area B, okay, current is being carried from here to here, the drift velocity here will be low, and here drift velocity will be high. Why? Because here area is low, so drift velocity has to be high, because A into VD is constant. And based on this, we have seen some KCET level question, and in board level model paper also does have some HOTS question on this. Okay, so this is VD is high, here VD is low. Okay, now what else? Current density is given by I upon A. So if you take A from here and if you divide it, I upon A is called current density, which is usually constant. So NEVD. Okay, NEVD is current density, and this can be represented as, if you put the value of drift velocity, it will be NE square by M into E into tau. Now if you see why there is a negative sign, by the way. The negative sign represents drift velocity, which is a vector quantity. The drift velocity is in the opposite direction of the electric field. So electric field is, if electric field is say along the x-axis, drift velocity will be along the negative x-axis. Okay, so that's why there is a negative sign. Okay, now J and E are in the same direction, so we are ignoring the sign of the VD. Actually, you can put the negative sign here as well. Anyway, we are not, because current is not a vector quantity, we are not using negative sign over here, but current density is a vector quantity, so that's why we are using this formula. Okay, so N is squared by M into E tau. Mobility, which is most important concept, mobility is given by drift velocity per unit electric field. Drift velocity is mobility is drift velocity per unit electric field, Vd by E. And again, if you put the value, you will get E tau by M. Conductivity is given by 1 upon rho, that is conductivity and resistivity, they are exactly inverse of each other. Okay, and it is given by J upon E, and it comes out to be N E square tau by M. This derivation is important. The derivation of this formula is important. If you want to know the derivation, we have done it during one of my Brahmastra lecture. You can go and check that out. Okay, now let's move on to the next concept, limitations of Ohm's law. So Ohm's law is, even though it is very good in terms of validity, but still there are some cases Ohm's law is not valid. One such cases is V ceases to be proportional to I. V is no longer proportional to I, and it generally happens at high and very low temperature. At very high and very low temperature, I is no longer proportional to V. So here we have taken the high temperature condition. So if you increase the temperature, the graph of V versus I used to be a straight line. Now as you are going in the higher range of current, the voltage is no longer proportional to I, so it is slowly bending towards the V graph. Okay, so this happens only at very high and very low temperature, normally for normal conductors. The relationship between V and I depends on the sign of V. This happens in case of semiconductor. Okay, this happens in case of semiconductor. For example, we have taken PN junction, forward bias and reverse bias. Generally, if the graph is a straight line, then you should get always a straight line no matter what is the sign of the V. Okay, so here as you can see, the graph behaves differently in the forward and reverse bias. So that means obviously Ohm's law is not valid in this case. And there is one more special case for some special devices. Okay, here you observe that for a single value of voltage, you are getting two different currents. Okay, here actually it is opposite. For a single value of current, it is possible to get two different voltages. Okay, so if you see from here to here, for each current you are getting two different voltages, but V proportional to I means if V is equal to IR, so for a unique V you are supposed to get a unique I. Understand this? Okay, so it is an equation. Suppose, okay, x equals to 5y. So if you put y is equal to 2, you are getting x equals to 10. But if it is x square equals to say 5y, then if you put say y is equal to 5, then x equals to plus minus 5 will be the answer. So that is not a unique answer. So you understand that it is no longer a simple straightforward proportionality equation, but it is a square proportionality. That's why this is also a violation of Ohm's law. So some conductors and semiconductors, they do not obey Ohm's law directly. Okay, at some range, certain range they do obey, but not completely. And at higher temperature and lower temperature, Ohm's law is not valid. Now let's move on. Combination of resistances, very interesting. So combination of resistances can be combined into two different ways. One is series combination. Series combination is when one conductor is connected after one. Okay, this is a series combination of resistances, and in this case resistance simply gets added algebraically. Parallel combination, which is slightly tricky. Okay, parallel combination is where conductors are connected like this. Okay, each conductor, in case of series combination, the current that is flowing in the circuit is same. Okay, but the voltage across them are different. Voltages are different. Okay, in parallel combination, however, the voltage remains same. the voltage remains same, current is different. Current is different. Okay, very important to remember. So in series combination, current remains same, voltage different across each and every resistors. In case of parallel combination, voltage remains same across each and every resistors, but current is different. Okay, parallel combination is most used in our day-to-day life, because the current electricity that is being used in our houses, it always uses parallel combination. That's why all equipments, all lights can function independently. Okay, there are in lower classes you have learned about the differences between parallel and series combination. If one bulb fuses, in case of series, all bulbs cease to glow, but in parallel combination, even if one bulb is fused, other bulbs will still work, right? Now, electrical energy and power, some few relations that you have to remember. This is also again basic relations. H equals to VIT, or energy equals to VIT. Energy equals to vitamin. If you forget, you can remember it like this: energy equals to vitamin. If you eat vitamin, you get energy. V into I into T. Now this can be converted into other forms based on V is equal to IR. So if you put IR, you get I square RT, or you can get V square by R into T. Okay, that formula we will learn more from power. So power is given by H by T into V equals to V into I, or I square R, V square by R. These are the forms of power. Okay, unit of electrical energy is joules, and power is joules per second, same as mechanical energy and mechanical power. Unit is same because it is energy, right? Energy is conserved, only it can change from one form to another. Okay, so even if it is mechanical energy or heat energy or current energy, the unit of energy is always same, right? So here is the resistance which is connected to a battery, and the resistance is something which is responsible to using that energy stored in the battery. So energy stored in the battery is in the form of chemical energy, which is converted into electrical energy. Clear? Now let's move on. Power rating of a bulb. Power rating of a bulb is very interesting point. If power rating of a bulb is given, voltage is given, then the resistance of the bulb is given by R equals to V square by P. Okay, bulb, generally we used to have this incandescent bulb. Okay, even though we are no longer using incandescent bulb, but still we are using the power rating system even for our LED bulbs. Okay, we have all seen this kind of bulbs, right? So this used to be the bulb that we used to use once. Okay, there is nothing much, only a nichrome wire there inside the bulb, and it was completely vacuum or filled with nitrogen. Okay, nowadays we use LED bulbs, so no such restriction is required. Only LEDs are fixed in a particular order so that we get a good amount of light, but it uses a less amount of power. Normal incandescent bulb, they used to have a lot of power, and the brightness was also not that good. But nowadays we are getting much brighter light, but using a very less amount of energy. So we have progressed in that sense. The current, maximum current in a bulb is given by P by V. So bulb or any electrical equipment, they basically have only one thing mentioned: 100 watt, 200 watt, 5 watt, 10 watt, like that. And generally it means that if you connect it with a 220 volt supply, that is our normal household supply, then it will consume that much amount of power. Okay, so if power is known, you can calculate the current from current and resistance from that given rating. Okay, so these are very essential to solve questions. Let's see one question. 3 bulbs, 40 watt, 60 watt and 100 watts are arranged in series with a 220 volt source. The maximum light is obtained from. So here we have 3 bulbs, and they are not connected in parallel, by the way, they are connected in series. So if it was in parallel combination, answer would be easy. 100 watt would be consuming the maximum power because it is connected across a 220 volt, so it has a higher power rating, so it will be consuming more power. Okay, so if you can calculate the power resistances of each of them, R1, R2 and R3, now because they are connected in series, what will be constant here? Current will be constant, right? Current is constant. So what is the power dissipated by the resistance 1. Power dissipated by resistance 1 is I square R1. Power dissipated by resistance 2 is I square R2. Power dissipated by R3 is I square R3. So current is same. So who will consume more power? The one who has highest resistance. The one who has highest resistance, right? So if resistance is high, it will consume more power, right? Because it is it is proportional to resistance. The power consumed by a bulb is directly proportional to resistance in this particular case. Now, so power rating is given, but voltage is not given. So we will assume that voltage is 220 volt. Voltage is 220 volt. So if a 40 watt bulb is connected across a 220 volt separately, individually, then it will consume that exact 40 watt power. If it is connected in series along with some other bulbs into a 220 volt supply, it will not consume the 40 watt. Okay, it will not consume the 40 watt, it will consume less than that. Okay, and that consumption is also proportional to its resistance. So if we can find the resistance of individual bulbs, we can say which one will consume more power. Now, mathematically calculation is not required for this particular problem, but in some problem if you see that mathematical calculation is required, then you have to do that. Anyway, so what is the resistance R1 for 40 watt? Resistance R1 for 40 watt is given by V square by 40, V square by P. V is 220 volt, we are assuming in our head. What about resistance for 60 watt? Resistance for 60 watt R2 is given by V square, same voltage, right? So they all should have same voltage rating. And 100 watt is given by R3 equals to V square upon 100. Okay, so if you see that who has higher resistance, who has lower resistance. So if you see that top portion or numerator, we say in mathematics, numerator is same for all the terms. Okay, so top of the fraction is same for all the terms, but denominator is different. Okay, so here we are, suppose this number is say 1000. 1000 divided by 40, 1000 divided by 60, 1000 divided by 100. Which one will be greater? Smaller the denominator, higher is the number. So resistance R1 is greater than R2 and it is greater than R3. So R1 is greater than R2 is greater than R3. So this is a conceptual question. Okay, mathematics is not required. Only thing you need to understand that resistance is inversely proportional to power. So whoever has lowest power will have highest resistance. Lower power means higher resistance, and higher resistance means higher power consumption. Higher resistance means higher power consumption. You can solve the entire problem using mathematics as well. You can calculate the resistances, then you can calculate the current, and then you can calculate what is the power consumed by each and every component. So in KCET there are two types of problems where you have to solve numerically that what is the, if the same question is asked, what is the power consumed by 40 watt bulb? So in that case the problem is at least 5 times longer than the length that we are doing. Now right now it is a conceptual question. You need to know the concept and apply it to find, okay, the resistance is more for 40 watt, so it should consume more power. So the power maximum light is obtained from 40 watt. So more power it is consuming means more light it will give. Okay, so that's how you can calculate it. Otherwise, mathematically you can calculate it. Mathematical calculation is not required for this question, for the fact we can determine which bulb will glow more brighter. Now you should remember, if similar question comes in your KCET exam, then you should remember whoever has smallest power, that element will consume more power, or that will be more bright in series combination. In parallel combination, exactly opposite. Highest power, higher brightness. Parallel combination, highest power, higher brightness. In series combination, lowest power, highest brightness. Clear? Now let's move on to electric cells combination. Electric cells also can be combined into two ways. One is series combination. Okay, in cells in series, the equivalent EMF is given by this formula and equivalent resistance is given by this formula. What is the meaning of cells in series? Suppose we have electric cell. Electric cell is the battery, that we in common term we say battery. Okay, battery is basically combination of cells. Combination of cells is called a battery. So it has more than one cell, then it is called a battery. Only one unit is called a cell. Okay, so we use it every day, starting from our remote, mobile phone, everything has a battery installed. Mobile phones generally have more than one unit, that's why it is called battery. Okay, your in your remote control you have two cells. Okay, then the combination of cells is also can be considered as a battery. Okay, so the cell generally has some EMF and an internal resistance. This internal resistance is not visible from outside. So what we do when drawing the circuit diagram, we show it on the outside. Okay, so this is how we show a cell. Okay, so far we have studied cell in our lower classes also, but in lower classes we have studied about ideal cell. Internal resistance was 0. Now internal resistance of a cell cannot be 0, it has to have some fixed value, and that resistance we generally show in series with the cell. Okay, so this what is the role of this resistance? This role of the resistance is same as the property of a resistance. Okay, it will consume some power, it will waste some energy from the cell. Okay, so this is basically a thing that limits the effectiveness of the cell, and the potential across the cell is actually different than its EMF. Okay, if you try to measure the potential across a cell, okay, then you have to find the current through the cell. And if you can find the current, the potential difference, terminal voltage, okay, terminal voltage is the epsilon minus I into R. So this is the formula for terminal voltage. If you know this, you can solve terminal voltage related problems as well. Okay, now if the cells are connected in series, series means same as resistances, one after another, then equivalent EMF becomes this. Now if one of the cell is connected in the reverse polarity, okay, if one of the cell is connected in reverse polarity, okay, then that cell has to be subtracted from this addition. Okay, suppose epsilon 1 plus epsilon 2 plus epsilon 3, but there is a something epsilon 4 which is connected in reverse polarity, then the equivalent EMF will be epsilon 1 plus epsilon 2 plus epsilon 3 minus epsilon 4. Okay, this is how you calculate if some cell is connected in opposite polarity or not. So polarity is important. Okay, you simply cannot add every time, you have to check if they are connected in same polarity or not. Normally if nothing is mentioned, then you can assume they are all connected in same polarity. Now parallel combination is same in resistances in parallel. So epsilon 1 R1, epsilon 2 R2, epsilon 3 R3. Okay, then the equivalent EMF is something complicated, but if you remember this way, this order, then you will be able to solve any question anywhere. Epsilon 1 by R1 plus epsilon 2 by R2 plus epsilon 3 by R3. Okay, and divided by 1 by R1 plus 1 by R2 plus 1 by 3. This is same resistance in parallel, and here simply not just adding, you have to also divide R by R1 by R2 by R3. Okay, this is how you can find the cells in parallel. Okay, now if multiple cells of same EMF are connected in parallel, okay, same EMF has and same internal resistances, then the equivalent EMF is equals to the exact value of one cell. Okay, so why we do that? For example, if you are connecting two batteries in parallel, okay, two 1.5 volt cells in parallel, okay, so in that case, suppose everything is same, then the equivalent EMF will be equals to exactly one of the cell. Okay, so remaining will cancel out, you can check that out. Okay, remaining you can take the EMF as common, resistances will cancel each other and you will get the same answer. So why we do that in many cases? Because it can produce a power for a longer duration. Okay, if voltage requirement is not that high, okay, we sometimes connect two cells in parallel to provide more current for a longer period of time, and cells in series are connected to increase the potential. Okay, most of our devices, electronic devices, they use, for example, this device has two cells connected inside it, okay, and they are connected in series. So if one is like this, another in opposite direction, then they are connected in series. Okay, and series is required to increase the potential, parallel is required for sustained duration of power supply. So these are the practical aspect. Next, the equivalent resistance in case of parallel connection is same as parallel connection of resistances. And again, if one of the cell is connected in reverse polarity, then you have to subtract it in the EMF section. Now remember, resistances will always be added. No matter in series or in parallel, resistances will always be added using the formula. Okay, for series combination R1 plus R2 plus R3 plus R4. But in case of EMFs, there can be plus and minus based on the polarity. Okay, I forgot to mention that in the last case. So if you consider the previous case, okay, where we are discussing the EMFs, equivalent resistance in this case will be R1 plus R2 plus R3 plus R4. Resistances will be added. Okay, but EMFs can be plus or minus based on the polarity, which is very interesting and important to remember. Okay, now current in the circuit can be calculated using this formula. Here R is the external resistance. So this combination, if you connect it across an external resistance, I am assuming everything is connected properly. And if you connect this combination across an external resistance R, okay, the current is given by this, and this formula is valid for series combination as well. Okay, and after you calculate the current, you can find the terminal voltage as well. Terminal voltage is epsilon equivalent minus I into R equivalent. Okay, so this is the value for terminal voltage. Now let's see one question. Small n identical cells, each of EMF epsilon and internal resistance small r, are joined to form a closed loop. One cell A is joined with reverse polarity. The potential difference across each cell except A is. So we have n number of cells, so each of them have same epsilon and same resistance. Okay, they are all connected to form a closed loop. But in between there is a cell which is connected in reverse polarity. Reverse polarity means negative then positive. Okay, one of them is connected in reverse polarity. Total number of cell is n. Okay, that means, and they are formed a closed loop. Closed loop means this combination still continues like this. So positive, negative, positive, negative, positive, negative, negative, positive. Then we have positive, negative, positive, negative, positive, negative, positive, and so on till n number of cells. So they are forming a closed loop. Okay, each of them are connected in series. Each of them have same internal EMF and same internal resistances, including this one. Okay. Now, what is the total EMF? What is the total EMF? The total EMF is given by how many cells are there? Total number of cells is n. How many of them are correctly connected in same order? One, except one, everyone is connected in proper order. So n minus 1 into epsilon is the proper order, right? N minus 1 into epsilon, everything is connected in proper order. But there is one which is connected in reverse order. So reverse order means minus epsilon. So imagine there are 100 cells. Out of 100 cells, 99 of them are connected properly, 1 is wrongly connected. So 99 epsilon minus 1 epsilon. So remember that do not put n over here, it will be n minus 1, because total number of cells are n, but one of them is incorrectly connected. So correctly connected is n minus 1, and that incorrectly connected also you have to subtract it. So basically you get equivalent EMF to be n minus 2 into epsilon. Okay, so this is the equivalent EMF. What is the equivalent resistance? Equivalent resistance does not depend on the polarity, so they will simply be added and you get n into R. Okay, so this is the total equivalent resistance. Now what is the current in the circuit? Current in the circuit is equivalent EMF divided by R equivalent, because there is no external resistance connected in the circuit, so R is 0, capital R is 0. So you get this as n minus 2 into epsilon divided by n into R. So this is the current in the circuit. So what is the voltage across the cell? Voltage across the cell is given by I into R equivalent. Okay, so because there is no external resistance, so this is how you should calculate the voltage across the cell. So voltage across the cell is not R equivalent, sorry, for one single cell, right? For one single cell it's resistance only. So you get n minus 2 into epsilon divided by nr into r. So r cancels and you get n minus 2 into epsilon by n. So this is the EMF across a cell. EMF across each cell is this much. So you are not getting exact EMF, but it's slightly decreased because of this. Now because there is no external resistance, the EMF you should not do epsilon minus IR. Okay, epsilon minus IR is doable only when some external resistance is connected. Here you have to use this formula. Now Kirchhoff's rules, there are two Kirchhoff's rules. First of all, junction rules or Kirchhoff's current law. It is at any junction, the sum of the currents entering the junction is equal to the sum of currents leaving the junction. Very easy. Suppose we have a train station, and if some trains coming in, then the number of trains coming in should be equals to number of trains going out. Okay, so if say I1 I2 are coming in and I3 and I4 is going out, then I1 plus I2 should be I3 plus I4. I1 plus I2 should be I3 plus I4. Okay, and this is basically because suppose say 100 coulomb comes from this side, 20 coulomb comes from this side, and if 30 coulombs leaves from this side, the remaining 90 coulomb should go in this direction. So total charge, total incoming charge per second should be equals to total outgoing charge per second. So this is a conservation of charge. Okay, this principle comes from the conservation of charge, because current is nothing but charge per unit time. So if you fix the time, then whatever charge is coming in, the same amount of charge has to go out, because charge is a conserved quantity, right, for an isolated system, and it's an isolated system. No, you cannot create any charge inside over here. Even if you can create, it will create a positive and negative charge. So you basically you can say this is an isolated system, and any junction is basically an isolated system, and the total charge that is coming in has to go out. Okay, so this is a direct consequence of conservation of charge principle. Loop rule: the algebraic sum of changes in potential around any closed loop involving resistance and cells in a loop is 0. This law is based on conservation of energy. Now basically what is the meaning of this? Suppose we have a cell of some internal resistance and we have some resistances as well. Okay, suppose a circuit like this, simple circuit. I am not taking a complicated circuit. So you take a simple circuit. Okay, current, say this current is I, this current say I1, this current say I2. And if you take any one of the loops, so this is say R1, this is R2, this is V, this is small r, so this is R3. Okay, if you take any closed loop means what? Suppose you are starting from here, you have to follow one single path and come back to the same point. This is called a closed loop. You cannot come over here and then you can go from this side and you cannot come back to the same point. That is not the way to have a closed loop. Closed loop is only when you are traversing entire path and coming back from the opposite side, then it is called a closed loop. Closed loop is this is called closed loop. Okay, open loop is this one. This is open loop. Okay, closed loop is when something is closing, starting point and ending point are same and the sense is also opposite. So if you are coming from this side, you have to go back from the opposite side, then only you can say this is a closed loop. Now if you apply Kirchhoff's law is basically an advanced form of Ohm's law. Ohm's law says that voltage drop across any resistance is V equals to IR. Right? So V equals to IR is for one single resistance. So Ohm's law basically gives you for one single resistance. Kirchhoff's law is basically an addition to that, and it says for all resistances. If you add IR, I1R1 plus I1R2 plus I into small r equals to V. That's what I was about to tell you, that closed loop, even though you are talking about closed loop, when you are adding the voltage drop across resistances, then at the end you should write equals to the potential difference. That will be slightly helpful for you to solve questions. Now remember, if you are considering the battery, if you are going in the direction of the current in the battery, then it should be equals to V. If you are going in the opposite direction of the current that is sent by the battery, then it will be minus V. Okay, suppose there is one more cell is added in the middle. Suppose there is one more cell added in the middle. So this is say R1, and we have so this is say R small r1, and we have a cell which is connected like this. We have one more cell here, and this cell is connected in the reverse polarity. So when you are going in this side, okay, what you have to do, so this is the same polarity, sorry. So this cell is trying to send a current in this direction, this cell is trying to send a current in the opposite direction. Okay, so that's why they are called reverse polarity. Suppose you are starting from here, you are going, you are reaching over here. Now you realize that this cell is trying to send current in the opposite direction. So in that case, what you will be doing, I1R1 plus I1 small r2 plus I into small r1 equals to V1 minus V2. Okay, so why V1 minus V2? Because this cell is trying to send the current in the proper direction and you are moving in that particular direction only. Whereas this cell is trying to send the current in the opposite direction, that's why there is a minus sign. And this conceptual clarity will be more clear when you solve more and more questions. I have done one exclusive live based on circuit theory. You can go and check that out on our YouTube channel. It is called KCL and KVL circuit theory. Okay, circuit theory you can search in our channel and you will get the live video where I have discussed this concept in detail. You can go and check that out. Now next, Wheatstone bridge, the derivation of condition of balance is very important. You can check that out in our Brahmastra series where I have done the derivation. And the condition of balance in a Wheatstone bridge is where this galvanometer is balanced. Galvanometer is not showing any deflection. That means no current is passing through the galvanometer. So Wheatstone bridge is a way where we have four resistances connected like a Kaju Katli. Okay, so one end, each side of a Kaju Katli is like a resistance. So if you consider that, then you can say this is a Wheatstone bridge. So here we have one resistance P, here we have another resistance Q, here we have another resistance R, and the fourth resistance is S. Generally, Wheatstone bridge is used to measure unknown resistances, which was very popular a few years back. Nowadays, this structure is already there in many of the instruments directly embedded, so you can measure the resistances directly without much issue. Okay, so here we have P, Q, RS, and the condition of balance is P by Q is equal to R by S. Conditions for balance is P by Q equals to R by S. P by Q divided equals to R by S, or P by R equals to Q by S. Only one way is fine. So remember, P by Q equals to R by S, or P by R equals to Q by S. Order has to be same. Okay, order has to be same, and this is the condition for balanced. Again, unbalanced Wheatstone bridge I have done in my circuit theory video. You can go and check that out. Let's see one question. Now, Wheatstone bridge can be modified and can be drawn like this way. So whenever you see this kind of structure, this kind of diagram, that means it's a Wheatstone bridge. You can take these 2 points and extend it, and you can redraw the diagram, and you will get a Wheatstone bridge. Now in case of a balanced Wheatstone bridge, if the Wheatstone bridge is balanced, then what we realize that there is no current in the galvanometer. Now we have to understand that this point where two resistances are meeting like this, where this weirdness is created, okay, you cannot use simple combination of resistances directly to simplify this circuit, because this resistance is creating a problem. This is neither series nor parallel, right? So this resistance is creating a problem, which is the galvanometer. And if the Wheatstone bridge is balanced, then there is no current that is passing through this galvanometer, and as we can see, R by R equals to R by R. That means this is a Wheatstone bridge and this is a balanced Wheatstone bridge, so no current is passing through this. So you can simply cut it and remove it. Okay, so this is basically not playing any part in the circuit. Okay, and if this is not playing any part in the circuit, you can simply cut it. Now you see this resistance and this resistances are in series. Similarly, these two resistances are also in series, and their combination is in parallel combination. So this is a very important trick that you have to remember. If the Wheatstone bridge is balanced, then this is a way to eliminate the unnecessary resistor, that is the galvanometer, which is creating a problem. Once this resistance is gone, everything is simplified, and you can solve this problem. Now, one more important part is if all the resistance of a Wheatstone bridge combination are same. So here, as you can see, every resistance is R. That means in that particular case, the equivalent resistance of this combination is exactly equals to R. Okay, if one of them is different, suppose R2R, R2R, then you have to use combination of resistances 3R, 3R, 3R by 2 will be the answer. Okay, now if one of them is different, say R4R, R4R, ratio has to be same first of all, and in KCET they will give you problem where it is a balanced Wheatstone bridge only. Okay, in fact in JE also they might give you a problem which is balanced condition only. Imbalanced Wheatstone bridge is may only be there in your PUC exam, not there in any competitive exam. Okay, otherwise it will take hell lot of time. Now, so combination of resistances you can apply to find the equivalent resistance once you have removed this, but in this particular case, if all resistances are same, the equivalent resistance should be simply be R. That is a shortcut. Similarly, here also you see that there is one more Wheatstone bridge. Okay, one more Wheatstone bridge. This is a Wheatstone bridge, one Wheatstone bridge. This is a second Wheatstone bridge. In this case, all the resistances are 2R. So again, this resistance does not play any role. This is a balanced Wheatstone bridge. Obviously, ratio of 2Rs must be same. So 2R by 2R is 1, 2R by 2R is also 1. So that means it's a balanced Wheatstone bridge. You can again remove this resistance. So again, the equivalent resistance of this combination is 2R. Why? Everything is 2R, so this should be 2R. Now we get a circuit where one is R, another one is 2R. They are connected in series. One side is plus V volt, another side is grounded, so the voltage difference is V0, and equivalent resistance is R plus 2R, that is 3R. So this must be the current in the circuit. So don't be afraid by the look of the question. The question is very simple and easy, and you can solve it in less than 10 seconds. So correct answer is V0 by 3R. Okay. So this is the end of the lecture, but formula sheet is added along with the lecture, so you can download the formula sheet and you can check the formulas. All formulas are given in single place, including drift velocity, current density, mobility, conductivity, etc. Also I have added formulas for resistance, resistivity, resistance, resistivity, and temperature dependence of resistance, series combination of resistance, parallel combination of resistance, and also we have energy and power formula. Okay, all formulas at one place. We also have Wheatstone bridge and electric cells combination, series and parallel. Everything is at one place. You can download this PDF from our WhatsApp channel. The WhatsApp channel link is given in the description section of this video, and if you download this PDF, you will get this formula sheet as well. And if you have not yet subscribed to our channel, definitely don't forget to subscribe. Obviously WhatsApp channel joining is mandatory, because if you want to download the PDF, you will not get anywhere else, right? I'll be back with one more chapter very soon. Till then, bye.